Landboards presents Under-Counter Kitchen Lighting, Breadboarding the Constant Current LED Supply. As a brief recap, if you didn't watch our first two videos, in the first video we selected an LED for the under cabinet lighting, and in part two we've selected and simulated a circuit to do constant current to the LED. Here we've built up the circuit from the on-semiconductor application note. The only difference is we've added a 1 ohm resistor in series with the LEDs, and we attached the voltmeter to that 1 ohm resistor. So whatever you see in millivolts on that voltmeter will reflect the current in milliamps. Here we're turning the supply up from 0 volts up past 10, and you can see the milliamps going through the LED circuit. Up to 12 volts it reaches about 13 or 14 milliamps. Our current sensor resistor in this case is 39 ohms, which differs from what we did in our simulation. If you notice, the goal that we were desiring of having a constant current as the voltage goes above 12 volts is achieved, because you can see that the current stays constant throughout this test at around 14 volt milliamps. By varying that base or the sense resistor, you can affect the brightness of the LED. Here we're doing the same circuit, but instead of driving the 3 LEDs on the breadboard, we're driving 3 of the LEDs that we purchased. They seem to get pretty similar performance, maybe slightly lower forward voltage than the other LEDs, which helps if you want to drive this at 12 volts. You can see the current here is about 13 milliamps. As we vary the voltage up, even as high as 18 volts, it drops down a little bit for some interesting reason. I don't quite understand why that doesn't show up in our model, but it does in a practical circuit here. But around 12 volts, it's around 13 milliamps. I think we'd like a little more than that. All in all, the circuit on the bench performs exactly like we would expect it to perform, and pretty much like the simulation performed. For the final test here, we replaced the 39 ohm sense resistor with a 22 ohm sense resistor just to get a feel for what the difference would look like. And the current, of course, is more current, as you would expect. It reaches about 25 milliamps. This isn't the 60 or so milliamps of current that the simulation showed, and not quite sure what the resistance or the difference is here. Perhaps it's having less ideal parts that makes the difference. This is about 75 milliwatts, which is well within the rating of the parts. In part 4, we'll build this circuit onto an actual prototype card rather than a breadboard. For more information, check out our wiki page. We also have a YouTube channel where you can learn how to use these products, and we sell our products on Tindy. Thanks for watching our video.